Hi, everybody. Okay, so we are going to move on with ionic and metallic bonding, and we're actually going to talk about ionic properties this time. Okay, and so for ionic properties, let me just scroll on over. There it is. Okay. So structures and properties of ionic compounds. If you look at this section of your notes, at the very top of that page, you'll see a bunch of pictures. So take a look at those pictures at the top of the page. These represent the arrangement of atoms within ionic compounds. And there are three ways that these can be arranged into crystal lattice that's shown in that very first picture, right? There's body-centered, face-centered, and just like your simple formation where it's the alternating pattern, okay? So take a look at that, read it over. Pause this if you need to, and then we're going to talk about how that crystal lattice creates some of the properties of ionic compounds. Okay, so ionic compounds are brittle, they're hard, they're rigid. They have high melting points, high boiling points. They're conductive in solution, conductive as a liquid, but not conductive as a solid. And we're going to talk about some of these more unique properties a little bit more in depth because it has to do with the way that the charges are arranged and also how strong those charges are. So ionic compounds are brittle, and the reason that they're brittle is that an undisturbed ionic crystal has a positive, negative pattern to the way its charges are arranged. No positive charges are ever together. No negative charges are ever together. But if you strike an ionic crystal, what you do is you actually align those charges at a molecular level to where that attraction between positive and negative gets broken because now you've misaligned it and you've got positive and positive together. And remember, like charges repel, and so that breaks apart the crystal. And that's really why ionic crystals are brittle. And it's the only reason that ionic crystals are brittle is that it's relying on the electrostatic charge to stay together. Okay. So the strength of the bond and the size of the ionic compound greatly affects the melting and boiling points, but ionic compounds are almost always higher in melting and boiling points than covalent compounds. So in this slide, if you look at the chart, right, you can see that you have some smaller ions versus some larger ions, and you can see the difference in those melting points. You can also see, like, if you look at the charge differences, like KBr is potassium bromate, and both of those are 1 charges. And if you compare those to magnesium and oxygen, which are 2s, right, 2 plus and 2 negative, you can see that there's a huge difference in the melting and boiling points in those, and that's because of that extra level of charge attraction that magnesium and oxygen has. Okay, and this plays into the lattice energy as well. Lattice energy is the energy required to separate 1 mole of an ionic compound into its cations and anions. Goodness gracious, we're having problems today. Okay, so lattice energy is also directly related to the size of the ions in the compound and how well their unbonded charges match. The greater the electrostatic attraction between a single cation and anion, the stronger the lattice energy is. And the smaller the ionic radius of the cation and anion, the stronger the charge will be. So something like a period 2 group 2 cation and a period 2 group 16 anion will have very strong lattice energy because the ions are very small and they have a large charge, right? They have a positive 2 and negative 2 charge. You can see this effect if you compare SrCl2 and MgO in the chart. So SrCl2 is strontium chloride. Oops. Goodness. And MgO is, of course, magnesium oxide. Okay. Sr is a much larger than Mg. Okay, so strontium is much larger than magnesium. And so MgO has over 1,000 kilojoules stronger of a lattice energy, even though both magnesium and strontium have that positive 2 charge. The other part to that is that the magnesium is bonded to a single oxygen, and so that's a positive to negative 2 charge difference between the single atoms, where strontium is actually bonded to 2 chlorines. So the charge on strontium is pulled in 2 different directions, which weakens that because technically it's making 2 bonds, not just 1. Okay. And so this would also make magnesium oxide harder and more rigid than strontium chloride. Ions are conductive in solutions. So if you've ever participated in sports, you've probably heard of electrolytes. Electrolytes are just ions in solution, and they're essential for the functioning of your nerves. Without electrolytes, your organs and muscles would not be able to receive the electric signals from your brain telling them what to do, like breathe, pump blood, or even move. Now, ionic compounds can also be conductive as a liquid because similar to the way that dissolving them in water, for example, lets those ions move freely, melting them also lets them move freely because remember, liquids can flow and move around and they don't have a definite shape, which means that those ions can also flow and move around and conduct electric charge. So when you melt an ionic compound, they become conductive because of those freely moving ions. An example of this would be liquid table salt. At some temperature, table salt does actually uh, turn into a molten table salt, and it would allow it to conduct that electricity. All right. So those are the special properties that go along with being ionic. And we'll talk more about ionic compounds in the next video.